Thanks. And the next speaker is Marcella Iannuzzi from University of Zurich. And Marcella is an expert in ab initio modeling of many different systems, and in particular metal of interfaces and metal water interfaces. And so today she will talk about physics and chemistry of metal water interfaces, and in particular H2. The title of her talk is H2O platinum interfaces by ab initio molecular dynamics.
Thanks, Clotilde, for the nice presentation. I hope you can see my slides. You confirm?
Yes.
Yes, perfect. Yeah, so it's a pleasure to talk to this very field of expert audience. And yeah, so I'm coming from background of simulations at the density functional theory level of surfaces and processes at surfaces. And in the past few years, we moved towards liquid solid interfaces, and we have done already quite some work on the specific case of water platinum interface, and that's the reason why I would like to focus on this for today. The aspects that we already heard, but so we will hear also in the next talk, so we have to face and the problematics we have to tackle when we approach the liquid solid interface, or let's call them the operating conditions that are specifically of interest in electrochemistry are a lot. And both from the experimental and the simulation point of view, it's very hard to obtain the right insight in the processes that are happening at the surface or the interface. From the experiment, it's also challenging because you have a very small quantity of material and a lot of things that are going on, and to get atomic resolution or time resolution at that scale is difficult, and therefore simultaneously it's difficult to compare with simulations. In addition, there is the complexity of the system, the dynamics, and all the processes that occur. So we, as I said, we focused on the metal water interface, and we looked at a few aspects, a few features of this interface. Obviously, to obtain a picture of the entire electrochemical cell, so that is the holy grail, but that's still far from what we can get. But let's try to understand from molecular dynamic simulation a few properties of this specific interface. Our approach is since a long time to use molecular dynamics, but starting from very different type of systems. So typically surfaces at the gas interface or vacuum interface, and then we looked typically at molecules as adsorption sites and processes, also looking at spectroscopy, spectroscopic fixtures. Oops, it moved by itself. And then we try to extend this also to dynamics. In doing that, then we approach the world of liquid solid interface, but we needed to extend the capability of our tools, molecular dynamics tools, or actually to use the work done by others. And in fact, I will discuss about a lot of methods that have been introduced by others, and we try to apply this method to enlarge the scope of our simulation. So in this respect, it's important for us to be always in contact with developer of new methods, or be active in the development of new methods. So in that respect, we are on both sides, so application, and we try also to extend the methodologies. And for doing that, here we also try to, today I will not talk about that, but to explore free energy surfaces, for example, using advanced, enhanced sampling, and to try to go beyond the capability of a simple or standard molecular dynamic simulation. The projects I will present today are all based on molecular dynamic simulation. So the sampling of the phase space, and that will be done. So it has been done at the density functional theory level. So with all the implication that it takes, because simulations tend to be rather slow, and to sample a significant portion of the phase space and to get ensemble averages, long trajectories are compulsory, are mandatory. But that is our way to study the systems, and in order to do that, we use the CP2K code, and that is a code that has a variety of features, and many new methods are either implemented directly on the code or are implemented in other codes that are interfaced with CP2K, and that is one of the strengths of this community that tries to be as flexible as possible. And as I said, the code has many features, and you can find nice descriptions of the most frequently used features of the code in these two review papers. In addition to the code, obviously, we need also computational resources. And so the simulation, most of the simulation that I will present have been done by us on at the Supercomputing Center of Switzerland. And then I will also briefly present some simulations done by the group of Chengcheng Xiamen University. Okay. So the first part of this results that I present is related to the behavior of water and CO co-adsorbed at the platinum surface, the platinum 111 surface. This is a rather interesting system, even though is a simple system, because it is a nice model system where we have a lot of experiments, and it has implications for heterogeneous catalysis and electrochemistry. And in addition to that, so we will look at the IR spectra of CO, and the CO molecule is often used as a label for vibrational signals in other systems, and therefore, so we started to study this interface with molecular dynamics. So the question came from rather old IR experiments that comparing the CO adsorbed at a dry in a dry environment to the CO adsorbed in an aqueous environment, observed this red shift of the CO stretching mode, and that was for a long time not clearly understood. So there was some indication, or there was some suggestion that this could be related to some hydrogen bonding of the CO, the adsorbed CO molecule that weakens the CO bond and induces this redshift. In addition to the redshift, also an enhancement in the intensity of the peak is clearly observed. This type of change is not related to a change in the adsorption site. Actually, the CO is adsorbed on top, and there are no indications. So if CO were be absorbed in another position, then the change in the frequency would be much larger. So the question was, so what is happening at the aqueous interface when CO is adsorbed, and why? So the frequency is a frequency shift. So our model is then standard platinum slab. We model with dynamics both the dry and the aqueous interface. And we tested the different coverages of the CO overlay in order to also include in the possible explanation an effect of CO-CO correlation, so the frequency correlation. In order to do this type of simulations, since this require quite long sampling time in order to get the IR spectra, we decided to use the method that has been developed by Thomas Kühne and is implemented in CP2K, that is a second generation Carparinello molecular dynamics. The advantage, okay, this is just a picture of the system where you can distinguish the CO molecule, the co-adsorbed water molecules here, and the first layer of water, so the water layer just above the adsorbed layer. So I want to just mention the difference between the standard Bohn-Oppenheimer molecular dynamics scheme that is used typically together with a DFT. That is based on the fact that at each configuration of the ions, of the nuclei, the electronic structure is fully optimized, and the forces are then calculated, and then the nuclei are moved. So you have a full complete optimization or SCF cycle at each positions of the ions. The difference for the second generation Carparinello method is that there is a sort of a prediction first of the next electronic structure, the coefficient of the multiplying the basis set function from the previous state. So you have a prediction step. Then you have one or a couple of correction steps that are based on optimization step of this self-consistent cycle. But then this is interrupted quite early in order to speed up the calculation. This is important in particular for metals, because if you go down to the full optimization, then you have to wait many iterations before the metallic electronic structure is optimized. And the fact that the forces, the forces that you get from this early stopped SCF are noisy, so they are not the Bohn-Oppenheimer forces. This is corrected by introducing sort of a white error. So you run actually a Langevin type of dynamics, and you can demonstrate that by tuning properly the friction, this gamma parameter for your dynamics, the forces, the error of the forces is as a Gaussian distribution, and the average of the error converges to 0. So then you have a rather good representation in average over the long run of the dynamics of the system. And then, but let's say at least one order of magnitude faster for what concerns the simulation speed. So that said, so we use this type of dynamics, and then we can run this system with quite a large amount of water, monitoring the dynamics of the CO molecules at the surface, and what happens also to the water molecules. What we observe at the different coverages is that increasing the coverage, there is a clear change in the water density profile. That this is the pink one is for the water oxygen. So is it a density? And at low coverages, here you see the carbon and the oxygen densities. So from the CO molecule, here is the water oxygen, and you see that you have this double peak because there are some water molecules that are co-adsorbed together with the CO, where there is there are available sites. Increasing the coverage, you see that this co-adsorption is reduced until it is not anymore there. The effect on the dynamic of the CO, you see here. So you see here the correlation between the CO bond and the platinum carbon distance or bond. You see that in the dry situation at low coverage and also at 0.25 coverage, so monolayer, you have that the carbon, the CO remain always at the same site, and you start having some hopping to a hollow site at a higher coverage. In this case, when you have aqueous environment, is that this happens more frequently and earlier, so also at a lower coverage. And this is in line with what has been observed also by experiment, that there is a downshift between the linear to bridge ratio in the adsorption. What happens to the spectrum then? Oops, I missed again the bottom. Okay. Here you see the IR spectrum computed for this type of simulation, this in particular for this coverage. And you see the CO peak here. So here there is a zoom. And here we distinguish between the peak we obtain in the aqueous environment and in the dry environment. And there is clearly this, both we observe the red shift and the intensity increase. This happens, the shift happens for the lower coverages, and we don't see it anymore for the high coverage, where actually the water is not anymore co-adsorbed at the surface. So there is, in fact, an important effect of the co-adsorbed water molecule, but it's not an effect of hydrogen bonding. Actually, we can say that there is no real hydrogen bonding between the CO, the adsorbed CO, and the water molecule in the first water layer. Here you see the two the two hydrogen, one of the two neighbors of oxygen, the hydrogen of the co-adsorbed molecule, here in the first peak, and in the the second part, and this is the hydrogen and there is no hydrogen, that it is hydrogen bonded here at this distance. Okay. So the reason for this effect is charge redistribution between the co-adsorbed water molecule and the CO through the platinum. So in fact, there is a charge donation of the co-adsorbed water molecule that it is back transferred to the anti-bonding states of the CO molecule. This weakens the CO bond and induces this red shift. Also the intensity change, so enhancement in the intensity can be justified by the presence of the water bulk, so behind the first adsorbed layer. And this is due to the enhancement of the field that is at the interface, and it's not possible to see this enhancement in the intensity if you just have one or two water layer. So you have the shift, but you don't have such an intensity enhancement. You really need the bulk water to be able to observe this enhancement in the intensity. So that is really an effect of the electrostatic field of the water. So the next aspect that we want to consider about this the water platinum interface is the reactivity of the interface. So it is possible to have water dissociation at the interface. This has been already observed clearly, changing the potential, so electrifying the interface, but at the within the double layer region, the water is believed not to react with platinum, and that would correspond to the potential of zero charge of this interface. In fact, simulation have been done at the water platinum interface. So as I mentioned before, in the group of Jun Chang, there has been a lot of work done on this interface, showing that there is a clear electronic interaction between the water and the platinum with a charge transfer that induces here a dipole. And the structure of this layer of water has been studied under many aspects. So, for example, it has been observed the formation of this sort of frustrated layer where you have formation of these rings that can be 5, 6, 7 member rings. This layer has a very low diffusion coefficient with respect to the bulk water, and this is, interface has been studied also under different potential conditions. So again, in the group of Jun Chang, there has been this study introducing in the water slab ions such that you can induce a negative charge at the surface. And this has been studied in presence of adsorbent hydrogen to determine several properties of this electrified interface. In particular here, the computational standard hydrogen electrode method has been used together with the second generation Carparinello method to sample this type of interfaces and to determine the differential Helmholtz capacitance here. that is being found in this range of potential to be constant, and in a good agreement with what has been observed again in this range of potential from experiment. So I would skip the results of this study. We can discuss case to move to instead what happens if we consider the quantum effects in water. And this is an important aspect because it has been already observed in bulk water that quantum effects are important. And in fact, if we would consider a purely classical water, then this would correspond to a pH, a very high pH here, that is not consistent to the reality, and that would be actually poisoning water. So the aspects that have been considered are many. So how the radial distribution function changes, which is the effect on the gap and on the density, electronic density distribution once you include in your simulation nuclear quantum effects. Also, the interface, there have been studies showing that the introduction of quantum effects change the dynamics of the water absorbed layer here. And allows the dynamics of the hydrogen that can more easily move among the absorbed oxygens, and that strongly depends on the material beneath. So actually here the discussion was about the lattice constant of the metal that can induce a different dynamic of the hydrogen. So quantum effects have been already taken into account. What we have done is also, again, for the platinum water interface, considering the full slab of water above platinum. In order to speed up the simulation, of the path integral quantum dynamics, that would require to have quite a number of beats in the ring polymer that represent each particle. We have used the correlated noise method that is based on a non-equilibrium Langevin dynamics, and has been introduced by Michele Ceriotti some time ago. So this allows to use just 6 beats for each particle in order to obtain a rather well converged path integral simulation. So the results of the simulations are showing that there is indeed some effects of the nuclear quantum treatment of the nuclei, in particular at the interface. So here we compare the bond distribution of the molecule of the water molecules as a function of the distance from the interface from platinum. And here you see that in Born-Oppenheimer dynamics, there is some fluctuation, obviously a little bit enhanced at the interface here in the close vicinity of the interface, but this is much more relevant if we use path integral. And this is happening at the interface is much less in the bulk water. So that these are some aspects of the simulation. As I said, 6 beats. And what this implies is that there is a certain probability that hydrogens are hopping from water molecule absorbed at the surface to a water molecule that belongs to the first water layer. And here is a little movie, but here there are some relevant snapshots that you see that first you have absorption of one molecule at the surface. Then this molecule starts forming some complex here with the neighboring molecules. Then the hydrogen can hop around in the first water layer, but it, at least in our simulation, it doesn't leave the first water layer, and this occurs in rather short time until it comes back to the original OH that is still absorbed at the surface. So we have observed this type of phenomena many times along our simulation, along our path integral simulations. And we have not observed anything of this in the standard BOMD simulation. Here is the definition of a collective variable that is based on the coordination number of each oxygen. And when this coordination number changes, this is the coordination of oxygen with hydrogen, from the standard value in the bulk of 2 and goes either to 1 or to 3, this means that there is a formation either of a OH or of a H3O. And as you see, this is how this coordination number change as a function of the distance gained from the platinum surface. And you see that this happens mainly at the interface. From this type of analysis, we can say that about 7% of the trajectory snapshot have the formation of this ionic species. On this basis, we can sort of determine the probability of having this ionic species. So actually the concentration of this species in the entire trajectory at the platinum interface. And we can evaluate equilibrium constant that tell us that at this interface, the free energy of this reaction is about 7.8 kcal. In bulk, this constant would be about 14, telling us that at the interface we have sort of acidic water. On the other hand, at the potential of zero charge conditions. On the other hand, these effects are very short-lived, and under these conditions, we have not seen real reactivity. But the question is, what happens if now we use an electrified model as the one suggested by Jun Cheng, and we add ions in the double layer? So that is our perspective. We have not yet done it, but I think that would be very interesting to do. As a comparison, just to finish up, we did the same with deuterated water, and we have not seen the same enhancement in the deformation of the ions. And we have done the same at the gold interface. And in this case, it's really this activity is absolutely not seen. So here you see the ions, the number of ions is always much smaller than 2, that it is sort of our threshold where we say, okay, this is the real formation of some ionic species. That means that there is an effect at the interface that it is strongly related to the electronic structure of the metal that we have. And that is was already observed that there is differences in this electronic charge transfer between the water and the metal, as has been already observed. And that is also observed here in averaging the density of state of the projected density of state of the two simulation with platinum and with gold, with obviously also the interface with water. And the position of the D-band center and this tail of the states of the water at the interface that is entering the band, so that is changing a little bit and being so different from zero at the Fermi energy. That is the way how there is this hybridization between platinum and the co-adsorbed water or the adsorbed water, and is not happening at the gold interface, so that is not activating the water at the gold interface. Okay, so this is about what I wanted to show, the different methods for sampling the water platinum interface. And it is just, so I would say, almost toy models, in the sense that it has been studied a lot, but it is our playground to really understand which are the tools that we have at hand to study these complex interfaces based on electronic structure calculation. We have, so I showed also a little bit of spectroscopy, but the idea is one can go beyond the IR spectroscopy or the vibrational spectroscopy, and we will hear anyway about spectroscopy in the next talk. And that are really the tools that we can use, because we have a direct comparison with experiment that so the experiments are moving more and more towards a good resolution of the interfaces, and they need tools to interpret the experimental observation. Very important for us is sampling. So I showed a couple of different tools that we use for sampling and improving our understanding of the phase space. And I didn't mention anything about enhancement sampling, but that obviously can be combined with any of these tools to study reactivity. In the end, the final goal that we have is always understanding and controlling with atomistic resolution the processes at the interface, and achieve the same insight that we already have at the vacuum solid interface, where we can really compare one-to-one experiment and the simulation. This said, I go to the acknowledgement. So obviously the University of Zurich and the group at the University of Zurich are my main collaborators. The work that is shown has been done mainly by Jingang Lam, so who got his PhD last summer, and with the contribution, very important contribution of Vladimir Rybkin. I briefly mention the important work done in the group of John Chang by Chabolet and collaborators in order to go beyond the potential of zero charge condition and study electrified water metal interfaces using the computational standard hydrogen electrode. Yeah, a big thank obviously goes also to the computational resources, without which we couldn't do anything, and the whole developer team of CP2K because of the contributions and all the nice methods that are implemented. And obviously I thank you for your attention.
Thanks a lot, Marcella, for your very nice talk, illustrating what we can really achieve with applying the most advanced methodologies to model electrified interfaces, the amazing detail we can we can get. I see already a couple of questions. Not sure of who is the first. We have Alexi and then Stoyan. I would say Alexi.
Oh, okay. Almost in passing, you mentioned about kind of dissociation of water molecules in H plus and OH minus in the double layer. For instance, we worked on the theory of ionic liquids where we have a lot of clustering between the ions of ion pair formation and so on. And we discovered both theoretically and with simulations that you can crack these clusters into ions in the electrical double layer, because it's nicer to be in electric field when you are a monopole than a dipole, so to speak. But these are different energies. The difference between being clustered and being free in ionic liquid is about kBT, thermal energy. For water, you have much larger energy. So my question is, for which kind of voltages that you applied across voltage drops across the double layer, you would expect that kind of significant effect that the water will be electric field induced dissociated?
Yeah, so in bulk, it has been already observed in bulk water that you can have dissociation by fluctuation of the electric field of a few fraction of EV. Here, now, did you see my slide? I'll skip this. This slide. So we indeed have, due to this interaction and interaction within the adsorbed water, the covalently adsorbed water, and the platinum, we have a fluctuation in the electric field. This has been, and this is electrostatic potential calculated via Mulliken charges integrated over the trajectory. So exactly at the interface, we have a fluctuation, so we have a change in the electrostatic potential, and then we think that is this the trigger to this very short-lived water dissociation. The idea is now to actually apply a potential by electrifying the interface, what is not done here. So here there's no additional external potential applied. It's just an effect of this charge distribution between the first water layer and the metal.
Yeah, but you cannot apply very large potentials because you will have electrolysis of water then.
No, but we don't need, so we don't want to apply very large potential. We want just to go over the standard range of potentials that here that are used for studying the system, and so these are standard potential. So we know that in the hydroxyl phase you have adsorbed OH, and in an under potential phase you have adsorbed hydrogen. So we are there in the middle now. So in this double layer region. And there we have not applied any additional potential.
But in the double layer region, when you apply the potential across between the bulk and the electrode, so to speak, right? What the potentials we're talking about, like half of a volt within that range, right?
So it is in this range between 0.35 and 0.25.
Okay, and already in that kind of double layer, you believe that the water will be some water molecules will be dissociated.
There is a certain probability that is higher than in the bulk water. Yes.
And how much higher?
That is so.
So effectively,
So it is equilibrium constant here is 5.7, corresponding to about a free energy difference of 7.8 kcal. So from this simulation, one can extract a sort of acidity from these numbers.
But there will still be non-dissociate water molecules in the double layer, of course.
no, there is a OH on the surface and a hopping hydrogen in the first water layer, not moving to the diffuse layer for the moment. So we never saw a diffusion.
Okay.
So I hope
So in the diffuse layer, you don't believe there will be a shift. Okay.
No.
Thank you.
Okay, then it says Stoyan.
Yes, thank you. Very interesting talk. And I am especially curious to ask a little bit about the water structures that you were showing, because I mean, a lot of times these kind of things is done in gas, they don't have the water, but I think here the water is key for a lot of the properties. And one particular property I wanted to ask was about structuring of water. So a lot of times actually at hydrophilic surfaces, but also at other surfaces, people find that there's not only one, but in fact, several very structured layers of water, maybe 2, 3, sometimes up to 5. So my question is whether you have seen anything about the water structuring beyond the first layer, and kind of a related question, maybe if you have something about that, whether the electric fields affect the way that the water structures in the first 3 layers.
Okay, so let me go to the slide here. That is not really the right one. I don't think I have. Yeah, maybe this is the best that I can show with, from the slides. Here you have the structuring of water. In fact, so this is the distributed, the density profile of the oxygen, the water oxygens, and a rather low coverage of CO. Not additional fields, nothing. And then you have these 2 peaks, because there is a first layer of adsorbed, so covalently adsorbed water, and they are quite structured in the sense that they form almost a very slowly moving layer. And then you have the next layer here that it is shown by this green, whatever is the color, molecules here in this model. And then you have this water layer are hydrogen bonded with the first water layer. Then you have a sort of empty space. It's not really empty, but the next water molecule are not hydrogen bonded with this layer, and they just point towards the bulk. So then you have this separation between this first sort of double layer and the diffuse layer of water. So that is what we observe. Other layering, no. So you see here that then quickly water recover the bulk density. So that is what I would say, that I can distinguish these 3 phases. So covalent bonded, the first layer hydrogen bonded to this molecule, and then this additional part of the water slab, and then bulk water.
Okay, I see. And when you apply the electric field, then do you actually see any changes in, let's say, that 3rd peak or not?
I didn't show anything when I applied the electric field. I didn't do. In fact, there is some here some examples, but that is not really the same, because here you have hydrogen at the surface and ions within the double layer. So that is again a different situation. But this fact that you have the ions at the double layer induces a negative charge on the surface. So it's like having an electrified interface. And then, but then, yeah, the structure of water here is affected by the fact that there are hydrogens at the surface. And in fact, you notice that the water doesn't absorb at the surface, because there is a repulsion from this hydrogenated surface.
Sure.
So that is not a good example for what you want to know.
I mean, I was kind of asking if it's okay, the question in general, not only for this particular surface, the platinum, but in your simulations, have you seen something like 3 layers of structured water? Because that's the assumption that many people make, and actually this is something borne out by experiments in FM, in other spectroscopies, where near the surface, especially a hydrophilic, so maybe not this surface, but if you have modeled hydrophilic surfaces, the first 3 layers are almost like ice type of structure, and then after that it's more disordered. So that's one of the things I was wondering if, you know, which simulations have actually the best for doing this kind of verification.
Well, yeah, why not?
Maybe not. Maybe not.
No,
I was
yes,
curious.
yeah. So, but this eyes, no, we studied several times water at now at interfaces, and the third layer, the third ice layer, I have not observed, in fact.
Yeah,
Okay.
this is certainly an interesting question, but okay, we need to, I think, to give space. I mean, Maria Laura wanted to ask a question, if it is very short, because we are already beyond, time, so.
Okay, I try super short. Very nice overview, Marcella. So my question is related to the first one from Alexei regarding the nuclear quantum effect on the dissociation constant. So which seems to be pretty large. So I was wondering on if you can give an estimate on how much actually is due to the quantum effect and how much is the effect of the interface in itself, because actually you compare directly with the standard 14, not something that is calculated at the surface, right?
It is due to the quantum effects, because we don't see this if we just do BOMD. So it is due. Okay, I understand what you mean. So what is due to if you have the same interface but without quantum effect, you don't see it, right?
Right. Yes, but actually you don't see, but you haven't measured. So I
Yes,
mean, my question is, okay, I can reformulate.
Okay, yeah.
So
the amount of
to the accuracy of the way you treat the nuclear quantum effect, or maybe a combined effect of the interface plus the nuclear quantum.
It is a combined effect between the interface and the quantum effect. So that's it's combined, because if you have just quantum effects on gold, you don't see this. So you have practically the formation of no ions. If you have just the BO on platinum, you also don't see it, but combined, you see it.
Okay.
And yeah, so that.
Okay, sorry, I think that we really should wrap up the discussion. It's very nice that there are many questions, but I think it's maybe you can continue the discussion afterwards.